Welcome to This Explainer. We hear a lot about artificial intelligence every single day, but today we're actually going to pop the hood and look at the engine running it. We are taking a focused, logical walk through the anatomy of an AI engine. Specifically, we'll be demystifying the core specs and the architecture of the Nvidia H200 GPU just so we can understand exactly how it powers these massive large language models from the ground up.
Here is our roadmap for today. 1. What exactly is the H200? 2. Hopper architecture and memory. 3. Tensor cores and precision. 4. NVLink multi-GPU scaling. 5. Why the H200 excels at LLMs. And 6. The complete AI system. Let's just start right at the fundamental basics of the hardware and work our way down.
All right, Section 1. What is the H200? Understanding the baseline hardware. So, to really get the H200, we first need to establish what makes a data center GPU entirely different from your standard computer processor. Let's dive into this. A CPU is a general-purpose processor. It's optimized for control-heavy tasks with complex branching. You can kind of think of it as a very smart manager handling sequential operations one by one. A GPU, on the other hand, is a highly parallel processor. It has thousands of simpler cores optimized specifically for numerical matrix math. Unlike the CPUs that manage your operating system, or even the consumer GPUs you'd use for playing video games, data center GPUs like the H200 are designed for continuous, high-throughput operations, running 24/7 in enterprise server environments.
Now, the headline specification of the H200, and this is a big one, is its massive 141 gigabytes of high-bandwidth memory, or HBM3E. When you're dealing with large language models, or LLMs, memory capacity is often literally the absolute biggest bottleneck you face. Having 141 gigs on a single card allows it to hold much larger models natively in memory, and that's crucial because it significantly reduces the need to split or shard parameters across dozens of multiple GPUs just to get the model to run at all.
But here's the thing. It isn't just about how much data you can hold. It's about how fast you can actually move it. And this perfectly illustrates the second part of the memory equation. The H200 boasts an extraordinary memory bandwidth of 4.8 terabytes per second. Yep, terabytes. High bandwidth is the secret sauce that keeps those massive compute cores constantly supplied with data during all those complex matrix operations.
Moving right along to Section 2, Hopper architecture and memory, let's zoom into the chip and package.
To really put this into perspective, let's just directly compare the H200 to the previous generation, the H100. We see a massive leap in memory capability here. We're going from 80 gigabytes to 141 gigabytes of capacity and jumping from 3.35 all the way to 4.8 terabytes per second in bandwidth. Now, the base compute capability actually remains quite similar between the two, but this massive upgrade was specifically engineered to alleviate the memory bottlenecks of AI workloads. The result? Up to double the inference performance for certain LLM tasks. Pretty incredible.
So how is all of this organized on the actual chip? Well, the H200 is built on Nvidia's Hopper architecture. Inside, the compute units are grouped into what we call streaming multiprocessors, or SMs. These SMs share a really large L2 cache, and the whole point of that is to reduce repeated trips out to the main HBM3E memory. To keep everything super efficient, the architecture prioritizes keeping data as close to the computation as possible. It uses a very strict memory hierarchy, fetching from the massive global memory, caching it locally, and then reusing it to save both time and energy.
Okay, Section 3, Tensor Cores and Precision, the math engines driving the operation.
Inside each of those streaming multiprocessors are the real heavy lifters, Tensor Cores. These are specialized units dedicated entirely to the heavy matrix multiplication required by AI. The really cool thing here is that the H200 supports multiple precision modes, which allows it to dynamically trade off mathematical precision for just incredible speed. For instance, in 8-bit floating point mode, or FP8, it hits up to nearly 4,000 teraflops of performance. By slightly lowering the precision of the numbers being crunched, which, by the way, is perfectly fine for AI inference, the chip achieves just staggering throughput.
Which brings us to Section 4, NVLink multi-GPU scaling, connecting the compute fabric.
Because let's face it, sometimes a single card just isn't enough. When a model is simply too massive to hold natively on one GPU, multiple GPUs have to communicate seamlessly with each other. This is where NVLink comes into play. It's Nvidia's high-speed interconnect technology, and it provides up to 900 gigabytes per second of bidirectional bandwidth between GPUs. To really wrap your head around that, that is roughly 14 times the bandwidth of a standard PCIe Gen 5 connection. There's literally no bottleneck there.
And this massive interconnect bandwidth is a game changer, because it allows up to 4 H200 cards to bridge together, basically acting as a single, unified compute fabric. Some of the major use cases for this include model parallelism, where a massive model is safely distributed across multiple cards. It's also absolutely essential for gradient synchronization, which is just how GPUs agree on updates while they're training together. Plus, it's great for handling excessively long context windows and processing massive batch sizes without completely bottlenecking on traditional server architecture.
Next up, Section 5, why the H200 excels at LLMs. Let's look at processing large language models efficiently.
So the absolutely crucial point here is how all of these specific architectural choices map perfectly onto the mathematical demands of large language models. At the absolute center of it all is GEM, or General Matrix Multiply. GEM is the core computational operation in neural networks. It basically takes incredibly complex tasks, things like attention projections and feed-forward layers, and reduces them down to the simple act of multiplying large matrices together and adding up the results.
Because LLMs rely so heavily on these GEM operations, the H200 does something very smart. It breaks these massive equations down into smaller, manageable pieces called tiles. By following these exact execution steps, it maximizes efficiency. First, it fetches matrix tiles from the main HBM3E memory via the L2 cache right into shared memory. Next, groups of 32 threads, which we call warps, load portions of these tiles into their local registers. Then, the Tensor Cores perform fused multiply-add operations on that data. And finally, partial results accumulate and are stored back to global memory. This specific workflow keeps data on the chip for as long as possible, keeping those Tensor Cores constantly fed and minimizing those expensive, time-consuming trips back to main memory.
Finally, Section 6, the complete AI system, bringing the components together.
While the H200 is undeniably powerful, it doesn't work alone, right? It forms a heterogeneous system alongside the server's CPU. To really understand this relationship, it helps to build a mental model. The H200 brings the massive memory, that 141 gigs of HBM3E, the extreme 4.8 terabytes per second bandwidth, and the highly parallel tensor cores to the table. In this partnership, the CPU is the conductor. It handles the high-level orchestration, the data preprocessing, and the operating system tasks. It gets everything organized, and then hands off the massive, parallel numeric tasks right to the H200.
So if you take away just one thing from today, let it be this summary. From an LLM perspective, the H200 is best thought of as a massively parallel matrix engine with large, fast memory, carefully engineered to hold and process large models efficiently. That is the core takeaway right there. It is a purpose-built engine to solve the memory and compute bottlenecks of generative AI.
Which leaves us with a pretty fascinating thought experiment as we look toward the next generation of data center architecture. As artificial intelligence models continue to scale exponentially in size, will the future of hardware engineering focus more on raw compute power? Or is memory bandwidth going to become the ultimate limiting factor? It's a great question to ponder as you continue exploring this space. Thank you so much for joining me on this explainer.